What I'm going to be presenting on is work I did collaboratively with Goswami. It was done with Santa Coloni and Ritwana Goswami, and it's basically finding the Regge-Wheeler equation for Schwarzschild space seminar for gravity. So a lot has already been said about modified gravity, and what I've listed here is the criteria needed to be fulfilled for any theory of gravity, considering the successes of GR. So it should have acceptable Newtonian and post-Newtonian limits. It should reproduce cosmological dynamics. So it should, have the observational content should be consistent with what we get from the CMB from supernova experiments, and it should be free from tachyonic instabilities and ghosts. And all this is within the weak field GR limit and weak field gravitational limit, and GR has already ticked all those boxes. Now, on 11th of February, so we got this news that gravitational waves have been detected, and by then there was a lack of observational verification for GR in terms of strong field, in the strong field limit. And so, thing is, now we've got something to describe gravitational waves, the strong field limit, and that means we've got to have stable solutions within your theory. And so does this mean there's going to be death of modified gravity? There's my thesis to be thrown in the trash. I think maybe I put it like this, the first talks, and could be somebody had talked about this and say maybe no, but I'm here to say that, well, as GRT subscribes to all this, I'll be talking about F-bar theory, which also is a T12 ones. So it's already just been said, this is the action for F-bar theory. It's a fourth-order theory of gravity, and with GR, you would have Ricci scalar there, but here we have the general function of the Ricci scalar. And so we vary the action with respect to the metric, and we get field equations, which we can write as we do for the Einstein field equations, where we've taken a huge fancy. We take all the extra curvature terms to the right-hand side, and we have this effective energy momentum tensor, which has curvature terms and effective standard matter terms. So those are your extra curvature geometric terms. So I've already said this. So the method I'm going to talk about is the covariant approach, which is different from the usual metric approach. So you've got your space-time, and you take a space-time splitting. You take one direction, the time-like direction, so you have this non-intersecting wild lines, which is the time-like congruence. And this would be singletoming the observer and having the average velocity of the observer at every point having a pole velocity UA. And you can define our projection tensors where UA is the projection parallel to the time-like vector, and HAB projects onto the 3-rest space of the observer. Okay. And so the structured equations will be such that you get your dynamics from the Ricci and Bianchi densities for your UA, the time-like vector, and you end up with these evolution constraint equations. And basically those are your field equations. And we also have to define two derivatives in the process. So we've got a time derivative, which I'll tell as dot, TAB, and you've got a derivative within the rest space, which is your D, which is orthogonal to the time direction, and that's your AJ to define your derivative on the rest space. So projected on the rest space. And also the energy momentum tensor, we have your energy density terms, the usual energy flux, pressure, and isotopic stress. Remembering that I'll put the tilde term because this is for your effective energy momentum tensor. There are temperature terms sitting in there. Okay, so we also go on to define your three volume element and our VII tensor components, which explain the non-local part of gravity field. So you have the electric vial and your magnetic vial part. And the kinematics comes from varying your time vector, your UAV, and you obtain your acceleration terms, your expansion, volume expansion, and with the twist or vorticity, and your shear terms. So basically, these physical parameters and variables define the spacetime. And we want to move on to spherical symmetric spacetime. So these are best suited to the 1 + 1 + 2 approach. Okay, so we had the first 1 + 3 where we split spacetime as time-like direction. We have a three-dimensional rest space, which is orthogonal to that time-like direction. And then we, in the 1 + 1 + 2, we split the rest space further into a preferred direction and a two space. Okay. So this is a method that was developed by Chris Clarkson and Barrett. And we introduced EA, which is the preferred direction within the rest space. Okay. And this is orthogonal to your time direction. Okay. So basically, this is what we had originally. You have UA and your rest space diagrammatically. And so you take the rest space part and split it further by introducing a preferred direction. And then what remains is your two space, which is also orthogonal to that direction. And then we have to introduce a third projection tensor that projects onto those two surfaces. So initially, we have the time derivative, and because we split this rest space, we introduce this. We now have a hard derivative, which is along EA, the preferred direction, and we have a delta derivative, which is projected onto the two surfaces, which I'll call the sheets. And so we obtain a number of variables, which we get from splitting the 1 + 2 variables, physical variables, and so we've got acceleration terms, vorticity terms sitting there. We've got electric vial and everything else just obtained from the space of the 1 + 3 variables. And for the kinematics, what we have is that moving along EA, our preferred direction, we obtain acceleration, twist, expansion, and distortion of the sheet, the two surfaces. Okay. So what I need to look at is locally rotational spacetimes. Right? These have a unique preferred direction, and so 1 + 1 + 2 is suited for that. And we go into the classification of LRS2, which are rotation-free spacetimes. They're locally rotational symmetric spacetimes that are rotational-free. So our variables are reduced from that, and because of the symmetries, we get down to just those, defining the spacetime. So we've got Regge scalar, expansion, acceleration, shear terms, and the electric vial scalar. And then to close the system of equations, because we've got a function of R, we get this extra degree of freedom, and so we need to add on this equation for R, for Regge scalar. Okay, so what we call the trace equation. I'm not going to go into the general back of theorem that's just been explain that. So I'll move on to the difference between the metric method and what I'm going to speak about. So in the metric method, you have this background manifold and the realistic or perturbed manifold. And the difference between the two gives you a perturbed quantity, right? But what's the problem with that is coordinate dependent, okay? So it's like taking coordinate mapping. And so the different choice of coordinates, you get something different in terms of your perturbed variables. But in the covariant method, it's a gauge invariant method. So it's independent of the choice of mapping. Okay. So what we have is, we have the background with vacuum terms, and in this case, with LRS2 spherical symmetric spacetime, we're left with expansion, acceleration, and electric valve terms, and here I'm parameterized them with R, the radial coordinate. And then we have fast order terms, which are the other variables that define the spacetime. And so we linearize the field equations. The perturbation method is such that we linearize the field equations about the Schwarzschild spacetime. Sorry, I forgot to say that this is basically Schwarzschild spacetime. Okay, and so we linearize by dropping any product of fast order terms. And then, because we've got spherical symmetry, we can perform a spherical symmetric spherical harmonics. We can apply spherical harmonics to the system, and we end up with a set of two sets of variables. So we've got odd perturbations, which are affected by frame dragging or rotation, and then we've got even perturbed terms, which are invariant with respect to parity transformation. Okay, so for the time part, we just take a Fourier analysis of the equations. And then let's go into gravitational perturbations, and we find that at large distances, so basically we impose that R naught here being Ricci scalar, constant Ricci scalar, when that's 0, when you're far enough, you end up with just plane waves as described in GR for the local part of gravity. And in general, we can always write our equations in terms of, we're looking for wave equation that's x double dot minus x hat hat. So double time, double space derivative. And what we end up with is an equation that looks like that, a wave equation that looks like that. And getting here, it's not that trivial, because you've got all these tensors and you have all these possible wave equations from these tensors. So you have to, it's sort of intuitive, but what we found is that you find some similarities for some of the tensors, right? Like the shear tensor, and so we're able to really eliminate the unwanted variables, and we ended up with an equation that looks like that, which has the shear and the electric valve part, giving us this dimensional gauge invariant, frame invariant traceless, transverse traceless tensor. If that makes sense. All right, so the even part of this equation is coupled to the curvature term. That's because of extra degree of freedom. But the odd part is just exactly like GR. Okay. So when it comes to the spin to our tensor perturbations, there will be no difference with GR. Okay. So this is basically our Regge-Wheeler equation. Okay. So we basically save that, and when we perform a harmonic composition, I think we end up with that equation down there, and with an effective potential. So it's a Schrödinger-like equation, right? And we also have to account for the Ricci scalar, trace equation that I talked about before, and there we get our scalar perturbations. We perform the linearization again, and we end up with a wave equation that looks like that for the scalar mode. Perform this harmonic analysis and end up with our Schrödinger-like equation that looks like that, with that effective potential. And basically, I'll call this effective mass term. Now, prime here, I don't know if I mentioned it, is a derivative with respect to Ricci scalar. if we're looking at black hole stability, the gravitational perturbation is just like GR, because you have positive definite potential, you have stability, but for the scalar part, we have to impose this condition in order to have a positive definite potential. Okay? And so what does this all mean? I mean, why do we really need these equations? So we look at the quasi-normal modes, which were done in the first experiment by Regge-Wheeler in 1970. And basically, you have a signal where you have an initial pass, which is emitted by the source, so this initial pulsing. And then you have this quasi-normal ringing, which has nothing to do with the Patar source. This is the source is from the, I mean, it's related to the black hole, and then it will decay the power will take, right? Now this is the area I'm interested in. And so these quasi-normal modes are basically solutions to the Regge-Wheeler equation, subject to the following boundary conditions. So you have to have outgoing waves at infinity and ingoing waves at the horizon. Nothing should be coming in from infinity, from the horizon, and nothing should be coming back from infinity to continue perturbing the system. Okay. Now the frequencies for the quasi-normal modes have a real and imaginary part. So if the imaginary part is less than 0, you have a solution that vanishes exponentially. But what we want is a solution that's damped with time. So you want the imaginary part of the frequencies to be greater than 0. For the scalar part, now what we found is the form of the scalar equation, wave equation, is basically like effectively the GR scalar equation with, GR equation with a scalar mass term. Okay. And not much has actually been done in terms of stability. We didn't really go much into it, but as far as this, that there's no energy radiating to a spatial infinity, if you have the imaginary part approximately equal to 0, and you have your wave frequency less than or equal to your mass term. Okay. So physically, the results we got was that the mass can be estimated for the scalar quasi-normal modes, because that's what we're using. This is the extra term we have. And the black hole mass has to be much less than 3 times 10 to the power 9, -9 solar masses. So pretty small. So you basically have a micro black hole. So it will be very difficult to take these scalar modes, right? And they're basically at subatomic scales. And to compare this with the LIGO results, which are 36 and 29 times this solar mass of the sun, the black holes that were detected. So basically, recap. So the plan is to utilize the 1 + 1 + 2 perturbational formalism to deal with space-times, right? And apply the formalism to gravitational wave propagation for Schwarzschild. So the first step was to define the field equations using the approach and linearize along the Schwarzschild background. And then we perform a harmonic analysis and obtain the governing system equations. We've got our Regge-Wheeler equation. And further on, we investigate features of this black hole wave equation. So in conclusion, we applied the perturbation equation, and we showed that for tensor modes, we have the same thing as GR. And the main difference was the appearance of the scalar perturbations. So I have to say that this is nothing new about what we do in terms of getting Regge-Wheeler equation for f of r gravity. It's only that so far the method has been a metric method. But what I've shown you here is actually a gauge invariant way of getting the same thing without having to invoke any marking coordinate choice. Thank you.
Thanks, Malik. Any questions? Okay.
One thing, we know that in F-Vargar particularly, one of the main differences that you have with GR is that you have additional polarization modes for your gravitational waves. Are you able to track this down with your Regge-Wheeler equation? So you know you have only two polarization for the gravitational waves generally,
yes.
right? But when you try to graph including F-Var, you have actually up to 6 polarization modes.
Yeah.
Do you see that in the equation that you have derived? Into
no, we didn't.
perturbation, or you didn't see it? Okay. Do you think it's possible?
It's possible, yeah. Once you've done the harmonic analysis, you can
see it.
Any more questions?
Do you think you could look for the microphysical black holes as a science?
Sorry. No. They would have evaporated because they associated a lot with primordial. Evaporated. Sorry?
You could recreate the conditions.
I'm not too sure. I don't think I'm not too sure. I don't know what to do.
Well, there's a remark. Well, your last conclusion probably is just well, clear conclusion from the appearance of an extra scalar amount in F-Vargar. So yeah, you can induce scalar perturbations. Well, any more questions? Okay, so next time,